Jeff. He is a Regents professor in mechanical and aerospace engineering, and he's part of Oklahoma State University. Professor is very veteran, very senior person of IBPSA community, and also have served IBPSA as a president in the past. And I'm very glad that he has agreed to offer a webinar on very important subject on thermal load and energy performance prediction, which is part of the book. Presentation is based on a book chapter, but he also will be talking about a little bit more, which is not part of the present edition. Hand it over to Professor.
Okay. Well, greetings from Stillwater, Oklahoma, where I rode my bicycle in this morning 9 kilometers in 17 degrees C, warm, warm weather, unseasonably warm at this time of year. So I'm going to talk about well, an overview of thermal load and energy performance prediction, but specifically, let's see here if I can make the screen advance. There we go. Okay, so I'm going to talk about what I think of as the heart of the matter. At the core of all building simulations is a simulation of the building at what we call either the room or zone level. And we tend to use the terms interchangeably, but a zone might be multiple rooms. It's usually would be a space that's served by one thermostat. And the fundamental physics of this is, it's the first law of thermodynamics, conservation of energy, although we often say heat balance because for the most part we're not converting between heat and work, so it's just heat that we're mainly concerned with. And then that's combined with sort of heat transfer rate equations, steady state conduction, transient conduction, convection, and radiation. And the level of detail for every phenomena that we discuss in simulation can vary a lot. And so it's sort of a challenge in terms of giving even a webinar on the topic. There's so many levels of detail that people have gone to, depending on what they're trying to simulate. That it's hard to give an overview. In fact, I guess I'll say right off that it's probably going to be a somewhat spotty overview. But what I'm going to try to do is to lay a framework for understanding how the room and zone simulation is done. For the most part, I'm just going to cover either the simplest possible methods for each phenomenon, or maybe nearly the simplest possible method. And everything I talk about can be described in a more sophisticated, more detailed, more computationally intensive way. It's whether or not you need that detail is depends on your problem. As the current president of IBPSA, Chip Barnaby, likes to say, is it works until it doesn't. So there's a lot of things we can do very simply until we need a more detailed analysis. And it's hard to say, certainly impossible for me to say, sitting here at my desk in Oklahoma, what level of detail you need in a general way. If we get to a specific problem, then maybe we could discuss that. So I'm going to start with discussing an oversimplified approach. I'm just going to first discuss this from a steady state perspective, because I think it's easier to understand the heat balance approach in a general way without getting into transient conduction at the same time. So we'll start with that, and then we'll move on to transient conduction. Okay, this isn't a graduate course in building simulation, and this isn't really a research seminar. We're covering anything in particular detail. It's just a broad overview. So see the book chapter for more. There's a lot of references to other work and more advanced approaches and discussion of them. Okay, so I mentioned this already, that a zone is one or more rooms, which it forms a control volume for the analysis. It's assumed to have a uniform temperature. So if you don't like that assumption, you can divide your building into more zones. or you can use a model that has more than one air node per zone. That's also possible. But what we're going to talk about is one where the room is what the air in the room is well mixed and has a uniform temperature, or multiple rooms. So if it's sometimes we do things like putting all the offices on the south side of a building that, say, on a certain floor, that they all face the same direction, have similar load profiles. We put those all in one zone. Okay, and for the air heat balance, which is one of the heat balances that we do, the boundary is usually drawn at the inside surface of the walls, window, ceiling, and floor. So it's the room air. Okay, and there are the method that we're going to discuss is called the heat balance method. At the end, I'll discuss a couple alternative approaches. One's approximation of the heat balance method, and the other is really just the heat balance method, but approached in a slightly more detailed way. It may not be so much difference to a user, but at least from how it's organized, it may be a little bit different. So for the heat balance method, when we say that, there's really three types of heat balances. There's heat balance on the exterior surface of the building. So that includes solar radiation that hits the building and so on. There's the interior surface heat balance, which also includes solar radiation, but it's been transmitted through a window first. And then the zone air heat balance. Right, and again, it's the first law of thermodynamics combined with heat transfer equations. And if we give an overview, this originally comes from a drawing that was done by my PhD advisor, Kurt Peterson. I've redrawn it, but the idea originally came from him, and it shows here at the top what we'll call the outside face heat balance. And that heat balance has to balance solar radiation that's absorbed at the surface, convection to the outdoor air, and then long-wave radiation, thermal radiation, to the environment, to the sky and to the ground. And it balances that with conduction through the wall. And in the general case, this is of course transient, but we'll do a quick example later where if we treat the conduction as steady state, it's much easier to solve. So I will show you that. Then here we have the inside face heat balance, and we have in this case shortwave radiation from lights, transmitted solar radiation. It's come through windows and now is bouncing around the inside of the room, being absorbed by the walls and floor and so on. There's convection to or from the zone air. There's long-wave radiation exchange with the other surfaces, and then there's long-wave radiation from internal sources. People, lights, and equipment are what we usually think of here. And then finally, there's an air heat balance, which has of course, it balances the convection between the surfaces and the room air. It has convection again from people, lights, and equipment. There is heat transfer associated with infiltration, ventilation, and exhaust. And then finally, there is, if the HVAC system is an air system, it'll provide cold air or hot air to the space, and this will have to be balanced also. So the balance of all these often takes the form, or usually takes the form, of solving for the temperature at the outside face, at every outside face, at every inside face, and in the room air. They all have to be solved simultaneously. And once we find those temperatures, then we can find all of these heat transfer rates for that temperature and for the, say, outdoor conditions at the time. So if we start with just considering steady state conduction, right, this is just Fourier's law in one dimension. The heat transfer rates proportional to the derivative of temperature with respect to distance. And for the non-transient case, we can actually give this just in terms of the temperature difference divided by the distance or thickness of the layer. And this shows a one-layer wall here, but then we often define a resistance. In the US, we have something we call an R value. So if I say R11, that's well, it'll be 3.5 inches of insulation or something like 87 millimeters of fiberglass bad insulation is R11, for example. But that's this distance or thickness divided by the conductivity. And then the heat transfer is just given by the area times the temperature difference divided by the resistance. And if we have multiple layers, right, then we can add these resistances in series as long as the layers are in series, and we can add the resistances in series. So the total resistance we can get from adding up the individual ones across each layer. Okay, for convection, the surface convection, as opposed to bulk convection, but the surface convection from each, say from each inside face to the room air, or from the outside face to the outdoor air, is given by what's sometimes called Newton's law of cooling, a convection coefficient H times the area times the temperature difference between the surface temperature and the surroundings. And depending on which way we want to define heat transfer as being positive, this can take it's either form, but it's just the temperature difference. Now, that's sort of, we described it that way. It sounds very simple, and it is if we know a value of H, right? The trick comes into finding H, right, which varies a lot. So there are quite a few correlations that have been published for convection heat transfer inside buildings and outside buildings, but you could say it depends on things like how much buoyancy is there, what the wind or airspeed is, what the geometry is. All right, and just as an example, for exterior surfaces, there let's see, recent review papers showed about 30 different correlations have been published. This is one for low-rise buildings by Yazdanian and Clems. It was based on the Mowat facility in California, and the measurements are, or the convection coefficient is given as a sort of geometric mean value of a buoyancy-driven convection term and a wind-driven convection term. If you look at these correlations, you'll find some that give only a wind-driven term, some even go to 0 if the wind speed's 0, which I could tell you from a simulation standpoint is a bad idea. But to just use it blindly, you don't want the convection coefficient to go to 0 if the wind speed happens to go to 0 anywhere. But in any case, this is a sort of one form. For interior surface convection, we have a wide range of regimes. We have natural convection or forced convection, depending on what sort of heating, cooling system we have. We can have laminar flow or turbulent flow in the room. Let's see, something's happened to my slide here. The watts per meter squared K came over here. Oops, sorry. Okay, there are, if you have an air system where you're supplying cold air or hot air to the space, right? There are many different ways of supplying the air. You can have a ceiling diffuser, radial diffuser that uses the Coanda effect, and the jet adheres to the ceiling and then drops down the walls. You can have sidewall registers or diffusers. You can have floor diffusers, slot diffusers. There's just all kinds of configurations. And likewise, even if you have a radiant heating system, you can have the heat emitters can be placed different places. You can have panel radiators that sit along the wall or underneath the window, or you can have heated floors or heated ceilings. I mean, there's different possibilities. So although there's been a lot of research done in this area, there really is no what I would call globally applicable set of models that will apply for any situation. In a lot of simulations, we use tabulated values, so certainly when we do cooling load calculations. And these, this is just an example. This is a similar table to this, appears in the ASHRAE handbook to this day, and it's based on work done in the 1930s, so it's not something that was done very recently. Okay, So for radiation heat transfer, well, we have either solar radiation or what we call shortwave, right? So in the, say, visible spectrum, wavelengths are comparatively short, and then above the visible spectrum we have, or with longer wavelengths, we have what we call thermal or long wave radiation. And the radiative properties vary with the wavelength. In fact, for many materials they vary continuously, but we usually use again a simplified model, which I call a two-band model, in that it treats solar radiation as having one set of properties and then thermal radiation as having another. For the most part, building simulations assume the room air is a non-participating media, so there's no absorption of radiation or by the room air or by the or emission of radiation. And that assumption's pretty good for office spaces, but if you have something like a stadium or something like that, it's not so clear. It's probably likely that the room air in a stadium could, say an indoor stadium, could have some significant participation. We, for the most part, treat everything as surfaces as what we call gray. That's where the properties are the same at all wavelengths, and also diffuse, where the properties are the same in all directions. But really with two exceptions. So the two-band model really means that solar absorptance can differ from thermal absorptance or thermal emissivity, right? And part of assuming that it's gray is that the absorptance and emissivity in the thermal band is the same. And then windows are treated as specular. In other words, the properties depend on the direction. So your window can transmit different amounts of radiation depending on if it's directly, the sun's directly incident on the window, or if it's coming at if the sunlight's coming at an angle. Okay, so when we're actually treating radiation inside the heat balance model, you could say it's very simple. For if it's an opaque surface, we're just going to multiply the incident solar radiation, that's this G sub T, and that would be beam and diffuse, by the surface absorptance. And so here's a table of absorptance values from the handbook. You can find more absorptance data than this, but not a tremendous amount more. So not every color of paint that you could possibly apply to a building will have a corresponding absorptance, nor will any layer of paint stay the same over time. As it gets dusty and oxidizes and so on, the absorptance will change. Okay, well, for windows, as you can imagine, it's a lot more complicated. If we either treat it either with well, again, everything can have its more detailed or less detailed models, but a fairly detailed model would have the absorptance of each layer of the window. So if you have a double pane window, each layer will absorb a certain fraction of the incident solar radiation, and the whole window assembly will transmit a certain portion depending on the incidence angle. All right, so those are the main things that are needed from a radiation standpoint, but there's more needed in terms of, for instance, if we have a double pane window, we have to treat the convection and radiation heat transfer across the gap, right? And of course that changes depending on if we have a low E coating or so on, and the low E coating affects the long wave radiation in the window. So there is more, but in terms of the short wave, it's mainly, these are what we sometimes call the optical properties of the window. For a more simplified model, we would just treat the solar heat gain with this overall solar heat gain coefficient, which really just tells us the fraction of solar radiation that hits the window that's then transmitted either transmitted into the space or is absorbed by the window layers and then enters the space after being absorbed. It's complicated, right? The windows, modern windows have, among other things, thin, spectrally selective films, not selected films, but spectrally selective films. And usually the properties of the individual layers are proprietary. So I went and looked last week at buying some new windows for our house, and you know, there's no possibility of anyone telling me what the properties of the individual layers, what even the emissivity of the low E coating is inside the window. And then if we have internal shading layers or things like window screens or Venetian blinds, that further complicates it. So we need to make some approximations. In practice, I would say if you're just designing a building using windows that you buy, you know, probably this simplified model is probably going to be the appropriate level of detail. If you're trying to design windows, then you know you may want a more detailed model. Okay, so this is an example of some window properties that were generated by the window. This is the Window 5.2 program. So it's, if you can see here, this is the angle from 0 to 90 degrees, and also the hemispherical properties that we could apply to diffuse radiation. This would be the transmittance of the window versus angle, and so single pane, double pane, and here's a low E coating and a double pane with a slightly thicker panes, but clear windows, so you can sort of see the difference. Then the absorptance, in this case, there's only one window pane. So we absorb right about 10%. Actually, it's not, doesn't change so much over the angle for that, but it will change more, say, here on this second layer where it goes from 0.06 down to 0.04. But anyways, that's the best sort of data we can get. And the problem with using the detailed model is just that if you go to buy a window, it's usually the case that you don't know exactly what the low E coating is, what its properties are, and these were generated by specifying specific coatings with specific parameters. Okay, we take all this information and we do apply this in a window heat balance. I'm going to talk about surface heat balances more, so it's hard to get maybe everything in perfectly logical order here, but in terms of the window heat balance, you know, we've got incoming solar radiation, convection heat transfer, and then long wave radiation at the surface, and depending on how much heat is absorbed, some of the solar will then pass through, some of it will be absorbed at the second pane, where it will eventually be convected or radiated into the space. This shows solar at the inside pane here also. Well, this is solar that's been transmitted through another window. And then in the inside, we have a radiative resistance and a convective resistance. And both of these resistances have to be, well, in fact, most of these resistances, depending on how detailed analysis we want, have to be recalculated at every time step because they're functions of the temperature. Say this radiative resistance is a function of these two temperatures, and so is the convective resistance. Okay, so still on radiation, on the shortwave radiation inside. Again, it's complicated. The simplest models is do something like assume that all the beam radiation that's transmitted through the window hits the floor, and whatever is not absorbed by the floor is reflected in that portion, and then any diffuse radiation transmitted through the window are assumed to be uniformly distributed to all the surface of the space. That's a simple model. And of course, there are extremely detailed models. If you look at, if you think of the extreme of models that render what spaces look like and give us nice visual images, those models keep very good track of where all the solar radiation goes and what everything looks like. So, you know, there's a wide range of possibilities here. But if we're doing energy analysis, there is this cost-benefit question, right? For the user, you could, of course, spend a lot of time specifying the location of interior furnishings, but those change. Well, in my office, they change a little bit day to day as the stacks of paper on my desk get higher. And then, you know, at the end of the semester, I may have a cleanup and the stacks of paper will get lower. But you know, where the chairs are and stuff, that changes from day to day. So, you know, question is, how much time should anyone spend doing things like modeling interior furnishings so we can keep exact track where the solar radiation goes? And again, it depends on what you're trying to find out. But there is a reason why simple models are commonly used. Okay, for long-wave radiation then, for the exterior surface, right, we have radiation to the sky, right? And the sky is an example of a participating media, right? We're radiating to the atmosphere for the most part. But that's usually treated as a surface with something called an effective sky temperature. We radiate to other surfaces. You know, it's usually simplified to be the ground, often at air temperature. You know, if you look around, if I look out my window, I see, you know, other buildings, and I can see a little bit of parking lot, and I see some green grass. I have a mix of things. It's not all ground. But typically when it's modeled, it's very common for people simply to specify that, say, a vertical wall will have a view factor of 1/2 to the sky. That's this Fs to sky, and a view factor of 1/2 to the ground, right? And if we write this expression out, the radiation that would be absorbed by our exterior wall, right, would be given by this equation, where these temperatures have to be in SI units, Kelvin, absolute temperatures, right? And so radiation is, I guess you could say, unique in that it's proportional to the 4th power of the temperature. But for building simulation purposes, we commonly linearize it, right? And so we get these terms here can actually all be reduced to a linear form. What that means, though, is that these values, as we perform the simulation and we iteratively adjust the surface temperature, the radiation coefficients to the ground and sky change. So, okay, and in interior long-wave radiation, again, we have the same problem, a cost-benefit analysis. How detailed should we be? So simplified models like the mean radiant temperature model. This is an example of a mean radiant temperature model where the network has been reduced to everything's radiating to this mean radiant temperature. Of course, in actuality, a 6-surface building has every surface has a resistance to every other surface. And if we do a full detailed enclosure analysis, it's even more complicated than that. I think if I do the math right in my head quickly, I think we'll have 41 different resistances, 6 for each surface, and then, well, yeah, I think that's right. But don't quote me on it. Okay, so looking at the clock, I'm seeing I'm using a lot more than 1 minute per slide, so I may have to move along a little bit. For what might be called bulk convection, but what we usually call infiltration and ventilation, right, we can calculate the heat transfer readily if we know the amount, right? So that's just m dot Cp delta T. The problem is knowing the amount, and that's discussed in Chapter 7, but I'll say under any circumstances, predicting the amount of infiltration is a difficult task. Okay, so I have an example of a steady-state surface heat balance. This is example 5.8 in the book. I've simplified it some for this, right? It's a very lightweight wall, so if we treat the wall as being steady state, we have just one resistance from the exterior surface to the interior surface, the U factor specified. The absorptance of the surface is 0.8 to solar radiation, and the emissivity is 0.9. It has incident solar radiation of 680 watts per square meter and outdoor and indoor dry bulb temperatures. The items in blue here they're worked out in the example in the book. What is the effective sky temperature? That doesn't depend on the building. These values here all depend on the surface temperature. And so in the book solution, we start with a guess and we iterate to these values, but I've skipped all that just to show that the steady state surface heat balance and looks like takes in the end this form. When we write out the heat balance and we solve for the exterior surface temperature, it takes this form shown here, where this is the solar radiation, the conduction, convection, and then the radiation to the sky and ground, right? And in our particular case, the outside temperature was what, 28, and the surface temperature, because of the sun shining on it, is 63.8 degrees Celsius. Okay, transient conduction heat transfer makes this whole problem a lot more complicated, right? We have resistances, but we also have capacitance that's distributed throughout each layer. I just took an example wall, and I'm sorry I don't remember any of the details of it now, but if you calculated it, the heat transfer as if it were steady state, the watts from this small wall would be something like this. But if we actually calculate the heat gain into the space after the effects of damping due to the thermal mass inside the wall, right, it delays the conduction heat gain and damps the response. So we see that the amplitude's lower. Okay, so historically the most common method used was conduction transfer functions. They're still used, I would say probably, well, I just have to guess, but I would guess a very high percentage, maybe in excess of 90% of all building simulations. But that's a guess on my part. But the conduction transfer functions are an elegant, computationally efficient way to do things. They depend on, if you here, this is the heat flux at the inside surface. It depends on the current surface temperature with this coefficient Z0 and past values of the inside surface temperature here, and then the current value of the outside surface temperature and past values of surface temperature, and then past values of the heat flux. So deriving CTFs is mathematically challenging. Using them isn't so bad, and it's fairly fast. But for actually quite a few years now, there have been some building simulation tools that say use a finite difference or finite volume approach to solve the conduction heat transfer. 30 years ago, we might have thought that was computationally infeasible, but it's quite feasible today. There are also lump parameter models that simplify the wall down to a few discrete resistances and capacitances, and often used if you're using something like MATLAB and you want a zone model. Okay, and there's quite a few exceptions to this 1D transient conduction approach, right? We have thermal bridges we have to deal with. We have heat loss usually to the ground via the foundation. We can have moisture transport, other phenomena that are important, and if we have, say, embedded heating tubes, cooling elements in the walls, all those things can complicate it, but we don't have enough time today to talk about those. See the book. Okay, the transient surface heat balance looks something like the steady state heat balance term that I showed you. But it's complicated by the fact that now the heat flux, say, at the inside surface depends on the current hour's outside temperature, and so on. So and the current hour's inside temperature. So just a little more complicated, and then all those historical terms have to enter into the equation also. Okay, so coming to the zone air heat balance, this is writing it out in a general form. We've got the convection heat gain to the space, infiltration heat gain, any gain due to the system, and any internal convection from lights, people, and equipment. Right? We can either cast this in several forms, or we can cast it in such a way that depending on what the coefficients are, we either have a fixed zone air temperature, or we can solve for the zone temperature when the system is off, or we can solve for the zone temperature and the system capacity. We can do this a couple different ways. There's what I would call simplified representation of the system that treats its capacity as a function of the zone air temperature, or with simultaneous simulation of the system. This is an example of a simplified system representation. So this is a variable air volume system where the negative part here is cooling, the positive part here is heating, and we have a piecewise linear representation that corresponds to when, say, the damper is opening and closing in the space, for example, here. And this blue line is the required heat transfer from the system at a specific hour to maintain the zone temperature. And of course, the solution is actually at the intersection of these two lines, although we don't solve the problem graphically. Okay, there are other zone models. There are thermal network models, which are it's a form of the heat balance model. It's derived in a different form. Practically speaking, it may appear to the user to be the same or not. Certainly, you can derive a heat balance model or thermal network model, for example, that has multiple air nodes in the space. So it's a little bit more complicated than what I discussed today. Also, transfer function models are an approximation of the heat balance method. They're close enough for most conventional buildings. And again, if I had to guess, in the US today, it's probably the most commonly used models use transfer function model for the zone. So to wrap up here, looking ahead, I expect to see continued evolution of the approach that I showed you. There's a wide variety of things that drive this. First of all, the wide variety or infinite variety in building designs. And as you change the building designs, not only the geometry, but the construction techniques and types of walls, the importance of various phenomena changes. So I would say for many years, if you had like an office building, we worried very little about the foundation heat transfer. It was just considered to be negligible. But as you do better and better job insulating the building and better windows, then the importance of foundation heat transfer, say at least on the ground floor, will go up. We get new building components and so on that require new approaches. So computers get faster. That's changed a lot of our approach, and I think we'll keep changing things. And finally, experimental research is still ongoing, and if you consider the problem of convection heat transfer that I showed you something from the 1930s, partly because we really don't have a complete set of convection correlations, there's still more work that needs to be done. So that's what I have for today, and it's a very spotty overview of the book chapter, but I hope you found it useful. So, Rajan, I'll hand it back to you for questions. Thank you.
Thank you, Professor. So far, I have two questions. One from Jerry, and Jerry, would be okay if I unmute you and you can ask a question? Okay, so let me unmute Jerry Fellon. I have unmuted you. You may ask a question, Jerry. Hello.
Hello.
Yes, we can hear you. Yes, please go ahead and ask a question. Hello. Okay, let me ask on behalf of Jerry Fellon. It says is asking that current models used for below grade heat transfer are recognized as lacking reliability. Could you please comment on heated and unheated slab heat transfer algorithms and how simulation tools can be improved upon?
Oh, well, it's a very good question, especially as to how they can be improved upon. There's been a limited amount of research on this. A lot of it's based on numerical simulations, which I would say, numerical simulations are very helpful, but only up to a point. So if you talk about things lacking accuracy, what I think is really two things. First of all, we probably need some more work in even from a numerical standpoint, more widely applicable models that are sort of suitable for computation time to be used in simulation. And then we need a lot of experimental measurements to validate the models, and so that we understand just how well they work. Without, say for me, it's probably been 5 years since I've looked at the state of the art, so I would hate to speak and say there's nothing available that's much better than what we have. But 5 years ago, I would say there were, the state of the art was that there were some other models that have been presented that seemed promising, but they lacked the data that would be needed to implement them in a simulation. So I hate to give a too vague of an answer, but it's more work and definitely more experimental research, more validation, more measurements of real buildings to confirm just how well they work. So thanks.
Thank you. I had trouble with my microphone, but you answered the question very well. But you also touched upon the fact that with above grade walls and roofs being better insulated, this issue becomes more meaningful.
Absolutely. I mean, you think about all the work being done, certainly for houses, to make houses that are, approaching net zero energy type performance. You can do all that above grade. Below grade, we have a lot of limitations, just in not speaking from a simulation standpoint, just from a practical standpoint. We can try to we can put insulation in. In some climates, it will be eaten by termites. It's hard there are certain things that are very hard to do. A lot of houses in my part of the country have a brick facade. It's very hard to insulate on the outside of a basement wall if you have a brick facade. There's just no good way to do it. So it's a difficult problem, and I think an increasingly important one. So I think more research is justified, but we'll see what happens.
Thank
Rajan,
you.
do you have? Sorry, go ahead.
We have another question. We have a question from De Cruz. De Cruz, I have unmuted you. Can you please ask a question to Professor?
Hello.
Hello.
Hello. Yeah. My question is about the radiation equation. I'm wondering what is the logic of that linearization? It is something that is common, but what kind of stability that brings in? Because once you linearize the t to the power 4, I'm wondering whether you put that instability into the coefficient h. So in the next iteration, if there's a variation, isn't it that we are making the h more unstable? Or I'm not really sure. Could you please explain?
Sure, I can discuss that. It's an interesting question. Here's what I'll tell you. My experience, and I've teach various classes in indoor environment systems. I teach a graduate class in building heat transfer sometimes, but I also teach radiation heat transfer at the graduate level. And for that particular class, we've looked at this problem of solving the zone model with using the fourth order model directly. And my own experience is that linearization makes everything much more stable. Same thing's true with radiation coefficients and convection coefficients also. But in the case of radiation, we have an iterative solution for everything. So if we linearize it, then our next guess can be very good, and we can approach a solution rapidly. If I try to actually solve say a complete set of equations with fourth order power form of the temperatures, and I try to solve that with, say, a nonlinear algebraic equation solving technique like Newton-Raphson. I find it's much slower, much less stable. Each iteration in Newton-Raphson it tends not to converge very quickly. So in fact, I find that the linearizing the radiation to actually be a great help in getting the solution to converge. And then because we iterate on that radiation coefficient, it typically, in my experience for the sort of zone models I've done outside of a building simulation program where we were just testing the modeling sort of independently, in 4 or 5 iterations, you have very accurate temperatures, to say 3 decimal places or something. So that's my experience with it. It's actually an aid to it. So I hope that helps.
Yeah, thank you.
Sure. You're welcome.
Yeah, we have third question from Ranavir Pratap Singh. Ranavir, probably you may ask a question to Professor. Ranavir, can you hear me?
Hello.
Yes, we can hear you. Please go ahead.
Hello. Sir, my question is, in radiation heat transfer slide, can you please explain the non-participating media? What do you mean by this term? And two-band model.
Okay, I didn't hear your whole question. I did hear explain the non-participating media.
So the question, yeah, if I may repeat, the question is, in a slide containing radiation heat transfer, please explain a non-participating media and also two-band model.
Okay.
Yes.
Thanks, Rajan. Okay, so starting with non-participating media, if radiation heat transfer, when the radiation, say if one wall is heated and heat's leaving the wall via radiation, if there's a vacuum, all that radiation then travels to the other surfaces and is absorbed or reflected and so on. And in a vacuum, there's no absorption of the radiation in the inside the room. It's purely a surface-to-surface phenomena. Okay, but with room air, because we don't have a vacuum, but we actually have air, and air has in it 2 things that absorb and emit some radiation in the wavelengths that are common for heat transfer in rooms. And that's it has a little bit of carbon dioxide and some water vapor, and both of those can absorb and emit radiation. All right, so if you were to want to model the radiation heat transfer in an extremely accurate way, you would include the effect of the gases in the room, the water vapor and the carbon dioxide actually emitting and absorbing. Okay, but in practice, first of all, when you learn radiation heat transfer, if you're a mechanical engineer and take heat transfer, you always ignore the fact that the air in the room can participate. That's what we mean by participating media. And actually, that's a very good approximation for most rooms in most buildings. And just the possible exception is if you have something extremely large, like I use the example of a stadium with thousands of people in it, lots of carbon dioxide, lots of water vapor, and long distances between the surfaces. In that case, the radiation given off by the gases could become important. But I think, in fact, as far as I know, there are no at least commercially available building simulation tools that actually treat this. It's typically ignored. So I hope that helps on participating media. Again, we assume that radiation is purely a surface-to-surface phenomena, and I think that's pretty good in most cases. Then on the 2-band model, right, radiation, if you plot the intensity of radiation from the sun, or what we would call the black body emissive power, you can plot it versus wavelength. And for the sun, the peak wavelength is about, I'm going to say 0.4 microns. I hope I'm getting that right. But it's the same wavelength that we can see. But but if you were to look at this plot, there's it's a little bit like a bell curve, although there's a, with a maximum at the visible spectrum, but there's the sun's emitting a wide range of wavelengths, and our surface, like a wall with paint on it, the absorptivity actually changes according to the wavelength. So a simplification of this is to treat like radiation from the sun as all being one band, and we take the properties, say, in the visible spectrum where most of the radiation is, and radiation from the environment or from a person or something like that, in other words, radiation that's given off at temperatures around 300 Kelvin, we treat that as a separate band. So we treat the two solar radiation and thermal radiation or long-wave radiation separately, but then within each of those we just assume a single absorptivity. For windows we assume a single transmission function versus the angle, the incidence angle, and so on. So it's a simplified model of what happens, but it's a little bit more complex because we treat the difference between the properties in the solar spectrum that are dominant from the sun and from the surroundings differently. So just to wrap up with one example, if you paint your building white with a glossy white paint, the absorptivity to solar radiation might be around 0.3, 0.25 up to 0.4, but somewhere in that band. But the absorptivity to radiation that's given off at, say, 300 Kelvin, in other words from the surroundings, is probably still going to be about 0.9. So there's quite a bit of difference in the absorptivity, and we treat those as two bands, which is why I call it a two-band model. Okay, so that's my answer. Long answer.
That's very helpful, Professor. We have a fourth question, but that's very generic question, which a person wants to understand the solar heat gain coefficient and U factor calculation. But I will provide him some information from various sources. So that's sort of end of this particular webinar. And I thank you very much for your time and efforts which you have taken to offer this webinar. Thank you from IBPSA, and thank you from all participants to you, Professor.
Thank you. Good luck with your building simulations, everyone.
Thank you. Thank you all. I'm ending the webinar right now. Thank you.